Hi, my name is Logan Yang. I'm a machine learning engineer. This is a video version of my article, Why Sigmoid? A Probabilistic Perspective. Why choose this topic? Because everyone who studied machine learning knows the sigmoid function. But the reason why its output can be interpreted as a probability is not very well documented at one place. Some people ignored this question and went on applying logistic regression without understanding the fundamental reasons why it works. For those who are curious and try to search for answers online, most answers they'll find are incomplete or sometimes misleading. In my opinion, this makes this topic a good data science interview question. I used to ask my candidates this question at my previous startup. It gives me some signal whether they take knowledge for granted without really digging into the core. In this video, I'm going to walk through the math and explain the logic along the way. Please also read the article if you want to check out more details. Before we dive in, here's the big picture. I will go through probability interpretation of linear regression, maximum likelihood estimation. I'll then use an example Gaussian discriminant analysis to lead to logistic regression. Thirdly, the main point of this article, latent variable formulation of logistic regression. After that, I'll compare it with an alternative, which is called the Probit model. At last, I'll introduce briefly the concepts of exponential family, generalized linear models, and canonical eigenfunction. Okay, let's start now. The reason for mentioning linear regression here is to see how we can look at it as a probabilistic model of data, and whether we can apply similar ideas on classification. We assume our target variable y having a form of a linear predictor plus a noise term. We assume this is Gaussian noise based on central limit theorem. Then we can write the error as the difference between the target and the linear predictor. We call this the distribution of y given x parameterized by theta. We're not actually conditioning on theta because it's not a random variable. It is the parameter to learn. Next, we define the likelihood function. The likelihood is a function of theta. When viewed as a function of y and x with a fixed theta, it's just a probability density function. But when viewed as a function of theta, it means that by varying theta, we can fit a distribution to the data observed. This process of finding that best fit is called maximum likelihood estimation, or MLE. In other words, MLE is the attempt to find the distribution that maximizes the probability of observing the data with the assumption of the type of distribution and its parameters. We further write it out as a product for individual data points because we assume independent observations. And we can take the log transform because it's monotonic. And now we have this thing called the log likelihood. To maximize the log likelihood, we need to minimize this term at the end. Other terms are just constant. This is the magic. What is this? This is exactly least squares. So what did we do? The reason linear regression uses least squares to fit the data is because it tries to find the best model that maximizes the probability of drawing our data from it. The probabilistic formulation of linear regression is not only an inspiring example for our formulation of logistic regression later, but it also shows what a proper justification for model design looks like. We mapped a linear predictor with Gaussian noise to the target variable. For binary classification, it would be nice if we can do something similar, such as map a linear predictor with something to the probability of being in one of the two classes. I'll show how to do that in section 3. But next, let's look at a motivating example called Gaussian discriminant analysis. Let's consider a binary classification task on 1D data where we already know the underlying generative distribution for the two classes. There are Gaussians with the same variance 1 and different means. 3, and 5. Let me give them both 50,000 data points, so they have equal priors. The best we can do is to draw a vertical boundary somewhere that separates the two classes as much as it can. It's visually obvious that the boundary should be somewhere around 4. Using a so-called generative approach, meaning that we know already the class conditional distributions, in this case 2 Gaussians, we can use Bayes' rule to get the posterior in this form. Since we already know the priors and the class conditionals, we can use this formula to compute the prediction like this. We can clearly see the boundary in the posterior. The red region is classified as class 0. The blue region is class 1. This approach is a generative model called Gaussian discriminant analysis. It models continuous features. You may have heard of its sibling for discrete features. It's called the naive Bayes classifier. Now, let's look at the S shape of the posterior around the boundary. It describes the transition of uncertainty between the two classes. Wouldn't it be cool if we can model this shape directly without knowing the class conditionals beforehand? But how? Let's work through some math. Notice that the red and blue curves are symmetric. They always sum to 1 because they're normalized in Bayes' theorem. Let's look at the red one. It's simply P C0 given x, which is a function of x. We massage the previous equation a bit by dividing the top and the bottom with the top to the following form. We can cancel the priors because they're equal and plug the Gaussians in for the class conditionals. So that you can see something nice is happening. We have a linear function of x inside that exponential function. If we set z to be negative 2x plus 8 and write it out for the posterior, it becomes this. This is logistic sigmoid function. If you ask why we added the negative sign for z, it's because we want p and z to be monotonic in the same direction for convenience, meaning that increasing z will increase p as well. Looking back at the flow of logic above, what really happened that made it possible to have a sigmoid form posterior and a linear function for z? So that will give us some insights as to when we can model the classification this way. For the sigmoid form, you see that it came naturally from the Bayes rule for 2 classes. It doesn't require the class conditionals to be Gaussians. There can be a family of distributions that have a similar exponential form fitting into the same derivation we came through above, as long as the outcome y is binary. The input x can have some flexibility in their class conditional distribution. Next, let's look at the linear form of z. In this example, we had 2 Gaussians with the same variance and prior. These are the facts that let us cancel out the priors and the quadratic term of x in the derivation. This requirement looks quite strict. Indeed, if we change the shape of our Gaussians, the decision boundary can no longer be a straight line. Consider the 2D examples here. If the 2 Gaussians have the same covariance matrix, the decision boundary is linear. In the second graph, they have different covariance matrices. The decision boundary is parabolic. What this tells us is that if we model the posterior directly with this approach shown above, this is called logistic regression, by the way. It has some pros and cons compared to the generative approach of Gaussian discriminant. Gaussian discriminant analysis is a much stronger assumption than logistic regression. But when the Gaussian assumptions are true, it requires less training data than logistic regression to achieve similar performance. But if the assumptions of class conditionals are incorrect, logistic regression does better, because it does not need to model the distribution of the features. There is an extensive comparison for GDA and logistic regression in the book Machine Learning, a Probabilistic Perspective by Kevin Murphy. I discuss GDA here only to show that the sigmoid function can arise naturally when we try to model a Bernoulli target variable along with some assumptions. Now let's go back and look at the question we raised in section 1. We designed linear regression by defining the linear predictor with a Gaussian noise term. Can we do something similar in this case of binary classification? It turns out yes, we can. Let's look at it this way. We define something called a latent variable, which is a linear predictor plus an error term. And we let the outcome y to be 1 when this latent variable is greater than 0. We call it a latent variable because it's unobserved, and it's computed from the observed variable x. So let's choose a distribution for this error term. We choose a logistic distribution. The cumulative distribution function, or CDF, of this logistic distribution is the logistic sigmoid. If you look at these two graphs, you may find the shape to be very similar to a Gaussian. So let's denote the latent random variable as y star, the linear predictor as z, and the CDF as big F. We can then write the probability of observing y equals 1 as p y star greater than 0. Rearranging the terms, we can see it equals 1 minus f negative z. We made big F the sigmoid function, so it's fz equals 1 minus f negative z. So we can write p to be the sigmoid of z. Okay, now we have reached the sigmoid form again. This gives us the relationship between the linear predictor z and the prediction p. The function f, logistic sigmoid, which is the CDF of logistic distribution, is called an activation function in the context of machine learning. The inverse of the activation function is called the link function, which maps the prediction back to z. It is called the logit. To recap, the derivation is essentially saying that if we assume the error term to have a logistic distribution, the probability of our Bernoulli outcome is the sigmoid of a linear predictor. If you look at the derivation closely, this formulation doesn't require a logistic distribution to work. It just requires a symmetric distribution around 0. What is a reasonable alternative? A Gaussian. What if we assume the error to be Gaussian? It actually gives us another model that works similarly as logistic regression. And it also does the job. It is called Probit regression. Comparing with an alternative model that is designed to solve the same task is a great way to gain insight into our subject, logistic regression, and its assumptions. As the previous section mentioned, the Probit model for binary classification can be formulated with the same latent variable formulation but with Gaussian error instead of logistic error. You may wonder why it's not as widely used as logistic regression, since it seems more natural to assume Gaussian error. One reason is that the Gaussian distribution does not have a closed-form CDF, and its derivative is harder to compute during training. The logistic distribution has a very similar shape as Gaussian, but its CDF, the logistic sigmoid, has a closed form, and it has an easy-to-compute derivative. Let's look at the derivation again and substitute the terms for the Probit model. The function phi is the CDF of Gaussian. Notice that we divided the terms by sigma, the standard deviation, to obtain a standard normal variate, and use the symmetry to obtain the last result, just as before. This shows that we can't identify theta and sigma separately because p depends on their ratio. It means the scale of the latent variable is not identified. So we set sigma to 1 and interpret theta in units of standard deviations of the latent variable. The only difference between the derivation above and the one for logistic regression is that the activation function is set as the Gaussian CDF rather than logistic sigmoid. The inverse of the Gaussian CDF is called the Probit, and it is used as the link function here. Probit regression is used more in biological and social sciences as a convention. It generally produces similar results as a logistic regression and is harder to compute. So if you're not a statistician specialized in this area, I would say logistic regression is the go-to model. There's another link function called the complementary log that can be used for the Bernoulli response, but I won't go into details here. If you're interested, you can read about it. Okay, now we have seen linear, logistic, and probit regressions so far. One of their main differences is the link function. If we abstract that out and make some additional assumptions, we can define a broader class of models called the Generalized Linear Models, or GLM. A GLM models the expected value of Py given x, in other words, mu, the mean. For linear regression, mu is just the linear predictor. Its link function is the identity function. But for other cases, Py given x can be of an exponential form or some other form. If we still want to use a linear predictor somehow, we have to transform it to match the output. To get to GLM, we first take advantage of a nice mathematical form that groups some of the most widely used distributions together so we can study their shared properties. Instead of looking at each distribution with their own parameters, we can look at a shared form. Some distributions can be massaged into this form are called the exponential family. Note that it isn't the same as the exponential distribution. Here, y is the target response variable we are trying to predict. Statisticians develop some fancy names for these terms, but what I'm focusing on here is the term eta, also called the natural parameter. The natural parameter eta is just mapping the outcome y in that exponential function to the probability on the left. Let's use a concrete example to show what I mean. For a Bernoulli target variable with mean mu, we can write Py equals mu to the y times y minus mu to 1 minus y. Massaging it further to the form of exponential family, we see that the natural parameter eta turned out to be the logit. The logit is also called the canonical link function for the Bernoulli distribution because of this formulation of exponential family. As we have seen before, the probit is also a link function, but it's not a canonical link function because it doesn't fall into the exponential family form here. With the exponential family and its natural parameter, we can define a canonical link function for our linear predictor according to the distribution of the outcome y. In this case, a Bernoulli outcome gives us the logit link and the logistic regression. You can use the same method to design your own GLM based on the type of your outcome. The exponential family gives us a lot of nice properties. One of the most important is that their log likelihood is always concave. Equivalently, their negative log likelihood is always convex. And their gradient-based optimization shares the same form, so we can always use some iterative algorithm to find the best fit, like gradient descent. Besides Bernoulli, some other famous distributions in the exponential family include the Gaussian, Poisson, gamma, the exponential distribution, beta, and Dirichlet. To pick the GLM for your machine learning task, consider the type of your target variable y. For example, if y is a real value, use Gaussian, that is, least square regression. If it's binary, use Bernoulli, that is, logistic regression. If it's a count, use Poisson, that is, Poisson regression, and so on. Now we have covered a lot of material that is comparable to an entire chapter of a machine learning book. Finding leads from many different resources and making sense of them is not easy. Hopefully, this video can serve as a somewhat comprehensive and intuitive answer to the question, why sigmoid, for those who had doubts. I believe that the goal of learning is not just knowing the how, but also the why, so that we can generalize our learning in real applications. If you find this video helpful, please like and subscribe. If you have topics you want me to talk about, you can comment down below or reach me on social media. Thank you.